Welcome. This is an introduction to InqVent. InqVent is a mechanical ventilation machine, or simply a ventilator. In this instance, it is a pressure-cycled ventilator offering full peak airway pressure. This includes resistive pressure, elastic pressure, and PEEP. It is intended for this COVID-19 emergency. InqVent is configured and monitored by a web-based user interface. Connections can be made from computers, tablets, and smartphones. Connections can be made directly to InqVent or through a local area network. Multiple devices can connect, configure, and monitor InqVent at the same time. Alternatively, one device, say a computer, can connect to many InqVents. With all these methods of connection, many options are available to aid and protect our healthcare professionals. Several scenarios come to mind. A nurse's workstation can be linked to many InqVents. With this situation, a nurse can simultaneously monitor many patients at a glance without having to put on virus protective gear and enter a room. In another scenario, and at the same time, another attendant can attach to one room's InqVent from the door, again not having to don protective gear. A third case, and simultaneously owing to the network ability of InqVent, monitoring can occur across the globe from remote locations. And finally, as you'll soon see, InqVent is powered by 12 volts. It can easily be integrated into an emergency vehicle's power system and monitored directly from an EMT's cell phone. Now, let's jump into the subcomponents that make up InqVent. This is InqVent prototype number 7. It is still in development and full functionality will be achieved in the coming weeks. Here is a breakdown of the major components. First up is the air supply. This is an off-the-shelf 12-volt air mattress pump. At peak output, it can supply pressure up to about 30 centimeters of water. As the common pressures needed for ventilation are around 10 centimeters of water, it has been derated to increase longevity and reduce noise. As you might imagine, these pumps are quite loud. It is expected that a lined sound deadening box could easily be made out of plywood or MDF. Next, we have the main InqVent unit. The housing is 3D printed using ABS plastic. This unit houses 2 air valves, CPU, and supporting Wi-Fi and electronic circuitry. This unit connects directly to and controls the air pump. The housing has connections for standard airway hosing. On this visible side, we have hoses to and from the patient, and on the other side, we have an exhaust that can be routed via another hose to an external filter, again to protect our medical professionals. Now we need to talk about lungs. Obviously, lungs come in many different sizes, and depending on conditions, different pressures are necessary. Using the web interface, all parameters will be configurable, including breathing frequency, inhalation rate, peak pressure, resistive pressure duration, plateau pressure, elastic pressure duration, and rest duration. It is expected that InqVent will be able to handle all extremes of patient requirements. For this demonstration and for baseline development, a breath volume of 500 milliliters at a peak pressure of 10 centimeters of water will be assumed, which brings us to the test lungs. Although we need a test lung for official ventilator calibration, the price of even the simple spring-loaded products were beyond our budget. However, we did not want to sacrifice pressure or volume accuracy. Fortunately, there is a simple and indisputable alternative which requires no calibration and is the baseline for which test lung products are measured. Maybe you took high school physics? You might even remember Pascal's principle. If not, it's real intuitive. Water always maintains the same level in a connected vessel. Pressure applied to one side causes the water to rise on the opposite side. Since the medical industry uses units of centimeters of water, it makes it very easy to illustrate using food coloring dyed water. As can be seen here, the relative heights of the water gives the exact pressure being applied. This test lung was 3D printed with one extra key feature. The cross-sectional area of each of the cylinders is 50 square centimeters. Thus, when the water is 10 centimeters high, as in this case, there is 500 milliliters of volume, our specified pressure and volume. At the moment, the user interface is rather simplistic, but over the coming weeks, nice real-time graphs that the industry expects and friendly configuration screens will be added. This particular screen shows some key values, in a development sense that is. The test will be activated by the tablet off screen, but you will be able to see the activities of the InqVent on this smartphone. In this demonstration, InqVent simply spins up the pump. You will see the blower spin up to 180. It will stabilize, and then it starts firing the valves to cycle between inhale and exhale. It will be on a 12 breaths per minute schedule. At the moment, it simply slams the valves open and then slams them closed. Subtleties of rates and holds are ignored at the moment, but again, this too will be added in the coming weeks. Here we go. As you can see, the pressure and volume defined by the relative water height shows InqVent is performing as asked. The user interface is also tracking the pressures and valve position. Let's summarize. InqVent offers medical professional protection, remote configuration, multiple monitoring scenarios, and small packaging. On top of those that we have discussed, it has several other benefits. InqVent can be built by any maker proficient with 3D printing, mild electronic board population, and Arduino programming. InqVent can be produced in small quantities for around $30 US. This includes all the electronics, 3D printing, pump, and power supply. And finally, InqVent's design will be provided for free. All parts list, 3D printer models, software binaries, assembly instructions, and technical support will be provided free of charge on the website inkonnet.com. Thank you for watching.